Alright, so let's learn how to sketch face portraits, and let's learn the case 1 where you have both eigenvalues are positive. So here I have given an example for you, a coefficient matrix. So the eigenvalue, first eigenvalue is 1, second eigenvalue is 3, the eigenvectors are here 2, 1, corresponding eigenvectors here 1. Okay, so your face portrait is purely depend on these eigenvalues and eigenvectors. What do you do? So let's first draw the xy plane. That is the first thing you do. Okay, now the next step is draw the half lines created by the eigenvectors. That means first draw the eigenvector. So when you say the eigenvector 2, 1, that means it's a position vector. That means this point is, so the first row represent x, second row represent y, right? So what is this? What is the point that this vector represent? 2, 1, right? When x is equal to 2, y is 1. So mark that point. So when x is equal to 2, y is equal to 1. So this is the point. Now draw the vector. Vector start from 0. This is a position vector. That's the vector pointing towards 2, 1. Now then, that's a vector. Don't draw the direction, okay? We don't know the direction yet, okay? Extend this line. So then we call it a half line. Okay, good. So now let's have a side note. This red color line is the eigenvector corresponding to the eigenvalue 1. So let's have that there because that's super important. Now guess what do we do next? Draw the next half line. So when x is equal to 1, y is equal to 1, 1, 1 is the point, right? 1, 1. So draw that line. So first the vector, and then I shouldn't say vector because we still haven't decided on the direction, but we already know it sort of. Anyway, these are two half lines. Side note here, this is the eigenvalue 3. Good. So draw the half lines. That's the first step. Draw the two half lines. Now the arrows. Now we want to decide the arrows. So when both eigenvalues are positive, what happens? Look at the solution. In the solution, okay, in the solution, we have e to the t and e to the 3t, right? Of course, because the eigenvalue 1 and eigenvalue 3. Now, the face portrait is the picture of what happens to the differential equation, what happens to the trajectories when time moves on. Okay, so that is the idea of face portrait. In this face portrait, you do not explicitly have time, okay, but you represent time. How? Now think, when e to the tt, e to the t and e to the 3t, when t goes to infinity, what happens to both of these functions? They grow extremely large, right? They approach towards infinity. I shouldn't say approach towards infinity mathematically, but they grow large. They grow exponentially large. And we know for a fact what is the equilibrium point. 0, 0, right? The origin is 0, 0. We know that for a fact. So what happens to the arrows? The arrows will move away from the origin, from the equilibrium point. Okay, so these arrows pointing away, they go towards, they extremely large, they go towards infinity. I shouldn't say that, but they are pointing away from the equilibrium point. That's a better way to put it. Okay, so when both eigenvalues are positive, they goes away. When eigenvalues are positive, because e to the t and e to the 3t, their graph look like exponential growth, right? When t goes to infinity. Good. Now we want to discuss the what happens to the other trajectories. Here's the hardest part to digest. Okay, now these solution trajectories, these solutions curves are like a table. So you have time and you have what happens. So let's say in the beginning of the time, okay, when the time is very small, what is the e to the t and e to the 3t look like when t is equal to small? The exponential growth graph is like this, right? So when t is small, this is t, this is y, it's like y is equal to e to the t, right? This is the graph. When t is small, your e to the t is still small, right? Still small. So where do you start your solutions? In the beginning of the time. It start closer to 0, 0. Do you get that idea? This is super important. In the beginning of the time, the solution will start near 0, 0. Right? Because e to the t and e to the 3t are still small. So you start from here, okay? The solution start from here. And later when time goes to infinity, they will grow extremely large, right? But now we have two half lines. We have two terms, e to the 3t and e to the t. Later when time is very large, who will resemble the most? The solution curves will behave or go parallel to one of these functions or resemble one of these functions. Who will it resemble the most? E to the 3t. Do you see why? 3 is a larger number than 1. E to the 3t is exponentially large than e to the t. So it's the dominant. E to the 3t is dominant. Do you see that? When t is large. When t is small, both of them are sort of same, right? But when t is large, they behave alike. When t is large, my bad, the e to the 3t is the dominant. So guess what happens to the solution? You start at 0, 0 because when t is equal to 0, everything is small. Then you resembles this blue line, go parallel to the blue line. Okay, here in the down also you start from 0, 0 and you resembles, you go parallel to the blue line, because blue half line is the line corresponding to the eigenvalue 3, the dominant eigenvalue. Okay, so now the rest of the curve trajectories will look like this. All right, I hope you get the idea. Okay, they go parallel to, when t is large, they go parallel to the dominant eigenvalue. Okay, in the start they very much behave same. Okay, this e to the 3t and e to the t. So that's the idea. So now this equilibrium point, we have to discuss the stability before we stop. So the equilibrium point is said to be, guess what? Stable or unstable or semi-stable? Unstable. This equilibrium point is unstable because you move away from the equilibrium point. Okay, or we say this equilibrium point is a repeller. It does make sense, right? Because it's repel everything, these equilibrium points. I don't want you, it push everything away. So this, when both eigenvalues are positive, crucial word both, when both eigenvalues are positive, the equilibrium point is unstable, it's a repeller. Okay, all right, so thank you very much. See you in next video for case 2.